All right. So I'm a last year PhD student at Aalto University, which is in Helsinki, Finland. My team consists of Professor Vesa Valimäki, Sebastian Schlecht, who is at FAU now, and Karolina Pravda. So this is my PhD team. And my topic is machine learning-based artificial reverberation. And during my PhD, I focus mostly on an algorithm called feedback delay network. And through it, I learned a lot about differentiable DSP and about audio similarity measures. But in the past, I worked also on acoustic echo cancellation, flutter echo synthesis, and in my free time, for what's left, I like to engage with community-driven realities around electronic music, mostly as a DJ and event organizer. So today, I'm gonna give a brief overview on feedback delay networks. I will go through some practicalities when it comes to designing the parameters. Then we will see how we can synthesize real room impulse responses using FDN and using also differentiable DSP. And then I'll try to give you a brief overview of what we can do in a more creative way using FDNs. My one motivation for being here is to present to you what's available, what's currently being researched in academia, and also I would like to understand what you would need from us and what are your wishes as audio developers. Okay, so this diagram shows you a brief overview of the main room impulse response modeling algorithms that are there. I try to be as comprehensive as possible, but if you're interested in knowing more about this, I will suggest to you the 50 years of artificial reverberation from Vesa Valimäki. So on the left, we have wave-based algorithms, which are considered to be the most accurate, but the most computationally expensive, because these ones try to solve the wave equations. So of course, it's really hard to get more accurate than that. Then geometrical acoustics. Here we have an assumption. We assume that sound propagates like rays. So this is valid assumption for high frequency, but not as much for low frequencies. So what you will usually see is a combination of wave-based algorithms and geometrical acoustics. And finally, my favorite, the others. And here we have modal reverbs, we have statistical reverbs, and delay-based methods. And here's where we find feedback delay networks. And these are the least accurate, but the fastest to run. So usually when you try to implement a real-time reverberator, you will always end up here. I didn't put convolutional reverbs, but there's also that. As just a different, there you will need the room impulse response, right? So that's, if you have the room impulse response, you know exactly which position you want to simulate, then that's done. If you have a convolutional algorithm that is fast enough, which is not always given. Feedback delay networks, I would say they date back to the 60s, even though this is the Schroeder reverberator is not yet feedback delay network, but we will see that there is a very tight connection between the two. So in this one, we have a set of parallel comb filters that are there to generate echoes and model the reverberation time through these attenuations. But a comb filter creates a sparse sequence of echoes. So we will need something to increase the density, and that's the series all pass. And yeah, these ones just spread the echoes over time. At the time, it was considered to be indistinguishable from natural reverb. Let's try it. Yep. Then from the 60s till the 90s, we see a lot of different algorithms that were proposed. But we can detect three common ingredients in these structures. So one is a feedback comp filter, a damping, otherwise how else can we model the reverberation time? And then all-pass filters to spread the echoes in a more like uniform way over the spectrum. Here I put brackets because maybe not all the algorithms have all-pass filters inside them, but they try to have an all-pass filter-like response. I wanted to cut the background section short because there's a lot of material out there. And this is not the first time that feedback linear networks were brought to ADC. And indeed, we have Casper and Ben talk from ADC 2023, where they presented some challenges in using deep learning to model reverberation using FDNs. Let's try to reverb. This is really really good tutorial on writing your first plugin using FDNs and other and scattering matrices. And then we have a talk from DAFX 2027, 2017, by Jean-Marc Jo himself. This is really good tutorial. And then finally, a seminar talk by Sebastian Schlecht. So if it's the first time that you hear about FDNs, maybe these are like a little bit too much, but I will start probably from the later two bonus. These are all on YouTube. Okay, this is the FDN structure that I will focus on. Was formalized by Jean-Marc Jo and Chain in the early 90s. It's a generalization of the parallel comp filter structure, because if you see here in the recursive loop, we have delays and feedback matrix. So you have in a comp filter, you have a delay and a gain. In this case, the delays are interconnected to each other through this mixing matrix. But we have more than that. We have input gains outside of the loop. We have output gains also outside of the loop. And then in the feedback path, we have usually an orthogonal mixing matrix and the attenuation filters. These are there to model the reverberation time. Then what you have to keep in mind is that feedback linear networks are valid approach for the modeling of late reverberation. So after the mixing time of your room impulse response. But what you can do to model the direct and the early reflections is to add an FIR filter, for example, here in the direct path. And then to map the overall spectrum, you will use a tone corrector filter. Ooh, I lost the pointer. Yeah, there you go. So this is an example of what you can get. So the reference room impulse response. Okay, it's not super long, but. Okay, in the following few slides, I'm gonna give you a few rules of thumb on designing the parameters. So the size n corresponds to the number of delay lines that we have. More delay lines gives you a denser buildup of echoes, reduces the comp-like artifacts, and it's more suitable for multi-channel and directional implementations. But of course, it's more computationally expensive. Here we see the effect that that n has on the echo density profile, which is the number and distribution of reflections over time. So let's start with a small FDN. It becomes like increasingly more smooth with n. Then the delays. This is maybe the most challenging parameter that to design. So they determine the echo density profile together with the size n, and they control the modal density. And for this reason, we have a set of quite strict, I will see them as quite strict rules of thumb. You should use co-prime numbers so that you are sure that you can achieve saturation of your echo density. They should be logarithmically distributed to avoid clustering of the pulses of the echoes in the output. And they should sum to at least 6,000 modes. This is backed up by perceptual test run by Matti Karjalainen. The number of modes coincides with the sum of your delays. And you should avoid strongly recirculating short delays. Why so? We can look at the spectrum here. Short delays will lead to fewer but louder resonances compared to longer delays. This example is a little bit subtle, but we have two delays here that are similar in the two FDNs, but the shorter delays are different. Here we have shorter delays and closer together in number. Here, they are more logarithmically spread. So these are considered to be okay delays. We can still hear some repetitions, but they are not as bad as these ones. So it's a bit maybe subtle, but if you're using long, late reverbs, you can hear it when you convolve it with voice or when you process it with dry voice, for example. Then mixing matrix. So the mixing matrix, also called as feedback matrix, controls the interactions between the delay lines. It's usually unitary. So one design choice or method when it comes to FDNs is to design a lossless FDN. So you will just like put the mixing matrix, which is orthogonal, without damping. And just to show you how the interaction between delay lines changes according to the mixing matrix, I have this equivalent diagram. So if you have identity matrix, you will end up with a parallel comb filter structure. If you have this kind of matrix, you will end up with a Schroeder reverb. And then in here, we have nested all-pass filters. But with time, we see that in literature that people came up with more specific designs. And for example, here I put only 4. We have first Adamard, which is considered to be the most dense. And then Householder, which is the cheapest, is like only 2 times n operational counts. Then the random orthogonal, which is the one that I use because I run some statistical tests, and it's just like really good default choice. And then tiny rotation metrics, we will see an application of it later. For more design, there is this really nice DAFX paper of my advisor when he presents his toolbox. And then finally, damping. So at the beginning, the idea was to extend the delay lines of a lossless FDN with a lossy delay filter, but it's impractical. So in practice, what is being done is to place filters and damping in the feedback path. This leads to a negligible error, but yeah, it's much easier to build it that way. How to find the attenuation that you given the reverberation time? You can just use this function. So -60, because T60 is computed on 60 dB decrease. So -60 over the reverberation time, or T60, times the sampling frequency. And this is the attenuation per sample. But our samples spend some time inside the buffer of the delays. So what we usually do is to scale those filters according to the delay line length. This structure and this particular filter gives you one single slope in the energy. We can see it now here. Yeah, so this is one limitation of the basic FDN. We will see later how to model multiple slopes. Okay, so yeah. Manual tuning is tedious. That's what I heard the most from people who try to implement their reverb algorithm using FDNs for the first time. It is indeed tedious. And when you are designing attenuation filters, you need a reference reverberation time, which is good if you have it. It's amazing. There are a lot of ways to estimate the reverberation time. Schroeder backward integration is the easiest. But it's not always available or reliable because of high background noise, for example, or because you have a reverberant signal, so for example, reverberant speech. So why don't we use the data-driven optimization by gradient descent to solve tuning of FDNs problem? For that, we will need a differentiable filter formulation. We have a few available. So FDNs are IIR filters. And for that, we could think of using backpropagation through time or instantaneous backpropagation. We could think of formulating it with like convolutional layers with linear activation and zero bias, but this is for FIR filters. So you will need to do a lot of simplification. Or we can use frequency sampling. So with frequency sampling, what we end up doing is to sample the transfer function. So this is the transfer function of our FDN on the unit circle. So we get uniformly distributed or linearly spaced complex frequencies. And we take all the frequency-dependent parameters in our FDN and we sample them. This is also an FIR approximation of our IIR filter. And if you're familiar with this method, you might know that it can lead to time aliasing. Similarly to sampling in time domain can lead to frequency aliasing. Frequency sampling, time aliasing, same thing. We worked on a method to mitigate this. So if you're interested in that, just ask me later. So for now, let's consider that this is good enough method. One challenge that I had to face at the beginning of my differentiable FDN journey was that common audio losses alone are not able to capture common FDN artifacts. So FDN comes from common filters. So they have a lot of coloration if they are designed poorly. So what we did was to use a combination of a spectral loss and a sparsity penalty term. So the spectral loss tries to push all the resonances as close as possible to 1, so that without damping, we are creating a white Gaussian noise generator. And the sparsity penalty tries to have dense feedback metrics to increase the density of echoes. And then we have reverberation time optimization. Here I'm using either the echo density curve or the multiscale spectral loss. For the second time, I will not go through this tutorial just yet. Maybe later, we'll see if we have time. But here, I prepared for a tutorial earlier this year, a short script that shows you how you can tune your FDN given a reference room impulse response. So there's no deep learning involved in it yet. You just have one room impulse response, and you run several iterations of gradient descent to find the parameters of your FDN given that room impulse response. And it's based on Flemo library, which is a library for linear and time invariant systems. Here we put a lot of different designs, filter designs, and you can connect them in series, parallel, recursion, and do all sorts of stuff. And we use it a lot for FDNs. Okay, so this is the most exciting part. It's like very recent work, and it's on archive, not yet published. But in here, you were like, okay, cool. We have our differentiable FDN, and we somehow proved that That's like promising. It's very promising. Sounds good. Oh, actually, sorry. Why it is promising? Um, because like with the colorless optimization, we can go from an FDN that sounds like this to without increasing the modes, without increasing the size, just by tuning feedback metrics and input-output gains. So this means that we can use smaller FDNs and make them sound smooth somehow. Okay, so go back to this. In this case, we wanted to generalize over a data set of reverberant speech. And we wanted to solve the blind estimation of room impulse responses problem. And so with Philip Goetz, who is the first author of this paper, we worked on a DDSP framework in which we have a neural network that, given the reverberant speech, it's able to disentangle speech and reverb and to map the input reverberant speech to DDSP parameters, so to the parameters of our FDN. This is the FDN that we used. So we have tone control, input-output gains again, all the parameters that we saw earlier. And for the direct path, we have one gain that essentially controls the direct to reverberant ratio and a short delay. I'm not learning the delays, and that's a big problem. We're still working on it. Yeah, they're differentiable, but I don't dare to learn them just yet. So this is an example given, this is the real room impulse response, and this is what we get with the FDN. We use the sparsity loss, and we use the multi-scale spectral loss to train it. And yeah, just to give an example, this is the dry speech, convolved speech, and speech process with the optimized FDN.
Visit my sister up in Connecticut, or we want to just, go visit my sister up in Connecticut, or we want to just, go visit my sister up in Connecticut, or we want to just, go.
This makes me super happy. Here we're using only 6 delay lines, so it's a rather small FDN. And there are more audio examples, and hopefully it will be published soon. Yeah, again, Philip Goetz did the deep learning magic using variational autoencoders and a lot of latent learning. Okay, so how? Ooh, oh, just 20 minutes in. Okay. Yeah, how can we use FDNs for spatial audio? And why should we use FDNs for spatial audio? So, because it's low in complexity, we avoid convolution, meaning we don't need to generate and store a lot of binaural room impulse responses or spatial room impulse responses. So, and this makes it ideal for 6 degrees of freedom rendering. So, in a standard FDN, we know that create a set of decorrelated signals, but all channels decay at the same room impulse response. Reverberation time. This is not a good representation of how real room work, because in real rooms we have inhomogeneous and anisotropic sound decay, and this plot shows you the deviation of the energy decay on the horizontal plane. So the energy decay is very directional dependent. If you're interested more about general knowledge or directional reverberation, I will suggest you the background section of Benoit Allarier's thesis. So Jean-Marc Jo proposed a binaural FDN in 2010. And in here we see, up here we have the classical FDN, but instead of having only one set of output gains, we have 2 sets of output gains so that we can create these uncorrelated signals. Then we have a coherence matching filter. We cross-mix the output of these filters, and then we have a tone corrector. The tone corrector is needed to fit on the spectrum of your impulse responses. You will need something to model the direct sound and the early part of the HRTFs. So this is what these two filters are for. What about directional FDN and more than just binaural? So here, again, this is another work by Benoit, who, by the way, Benoit is now at IRCAM and he keeps working on it. And he works on SPAT. So if you're using SPAT and directional FDNs, sorry, directional reverb in that, probably there is some FDN magic in it. Yeah, so for directional FDNs, we have to rely on multi-channel delay lines. So here, the diagram uses thicker lines to show you that that's a multi-channel connection. We have n groups of Q delay lines, and each channel within a group corresponds to an incident direction on a spatial grid of Q directions. So you can use like the T design, for example. The channels can be defined as plane wave distributed around the sphere or around this like on this grid of directions. But there is a version of this FDN that uses spherical harmonics. So instead of having the attenuation gains be dependent only on the frequency, we have to include the azimuth and elevation. So these are here you have here you have Q different filters, one per direction. And then for the output, you can use different encoders depending on what type of format you want to use. So you have like ambisonics, bebop, HRTFs. Okay, this was presented 6 years ago, and so it doesn't use any machine learning, just as a disclaimer. Left, we have the directional energy distribution in the case of image source method, which was used as a baseline for this. In the middle, we have conventional FDN with single channel delay lines and a weighted directional input. We see that it's like rather, it's not super uniform, but it's rather uniform along all the directions. And then we have the directional FDN that is designed to resemble the image source method. It's not perfect, but at that time was like a big step for FDNs. And I'm hoping that with machine learning, we can improve this a lot. One other method is based on an idea, well, it's not just an idea, it's like a kind of like proved approach. That in a room we have, in rooms or like complex geometry, we can detect 2-3 different decay rates or like one decay rate per room. So that's a way of simplifying how energy decays in a complex geometry. In this case, we have like 3 different rooms. So we know that with an FDN, we can model only one decay, one slope. So what about interconnecting multiple FDNs together? And this is what Orchi-sama does postdoctoral research at King's College London did. So she presented this position-dependent, well, position-dependent comes later, but she presented this grouped FDN concept. So the structure is very similar to an FDN, but we have multi-channel connections. And in the feedback matrix here, the block diagonal matrices are the control the mixing within the room, and the off-diagonal matrices control the coupling between the rooms. That's like a way to interpret it, and also a way to design it, because you can design the matrix based on the coupling that you want to model. What it creates is just like in case we have a diagonal matrix here, you will have three distinguished slopes, and you will just like sum them up, and you will get like something like this grayish curve. So what we did, Orch and I did this summer, was to add a little bit of deep learning in it and machine learning. So we were like, okay, let's interpret the channels as the channels of the spherical harmonic. So we have n groups of q delay lines, and the number of q represents of like the number of channels that you would need in ambisonics for a format, for example. And let's take the listener positions and try to estimate the spherical harmonics gains here for the receiver and for the sound source as well. So we have two MLPs. Here we give to the encoder that controls the MLP, we give the source position, the receiver position, and yeah, we train it to minimize spectral deviation, promote low sparsity. So this goes back to the colorless optimization that I presented earlier, and too much directional energy decay curves. These were just a few examples of how to use FDNs for spatial audio. If you're still around and you haven't already, check out Matteo and Joshua's poster, which present a different way. It uses FDNs, but it uses a concept of acoustic radiance transfer, which is super interesting stuff. And they have a demo, which is quite impressive. And it will show you dynamically how, it will show you how the energy decay curves change when you change the listener position. So very cool demo. Okay, not a lot of time left, but let's try to show to see how you can use FDNs more creatively. One way is to add some time variation. Why time variance? If you're coming more from the physics world, you might think, yeah, time variance, you might need to model air movement from temperature or from physical interactions. They exist, and if you want to get a more accurate, physically accurate model, you want to model these subtle changes. But time variance also improve perceptual quality because they break up temporal patterns. They improve stability in reverberant enhancement system that I will explain in the next slide. So one option to add time variance would be to modulate the gains in FDN that it's like equivalent to an all-pass filter. But this leads to a risk of energy growth and ringing. So it can lead to instability pretty quickly. So instead of modulate the gains here, let's modulate the feedback matrix while keeping it orthogonal. And in this way, we are modulating the zero and pole locations. And we can do it safely by multiplying the orthogonal, by updating at each time step, the orthogonal mixing matrix by a tiny rotation matrix. This can break repetition, and it's quite a really nice effect. So here we are looking at the frequency of modes. For illustration purposes, here Sebastian used very few modes. Otherwise, it would be too chaotic to say. So we have slow synchronous modulation, fast synchronous modulation, and fast asynchronous. So this is slow modulation. Slow asynchronous. And the latter one was fast, synchronous. It's an effect that I would like to work on, and maybe we can do also with something with machine learning. We can go a little bit crazier. Of course. Yeah, reverberant enhancement systems. Yeah, real quick. So in this case, you have, in a venue, you have a lot of speakers that are placed around the venue itself. And beside the stage microphones, you have ceiling microphones that pick up the room acoustics and the signal that is being played through those speakers. And the idea is to give to the audience the perception of being in a different space by processing the microphone, the system microphones here, using an FDN. And so you will add this like virtual room on top of the physical room. And this is what my colleague Gianmarco De Bortoli is working on. And you have many different ways of implementing this virtual room. So random mixing metrics, FIR filters, multi-channel phase cancelling model reverberator if you want to have like a more controlled environment, and multi-channel unitary reverberator, and of course feedback delay networks. And we can use the coloration, the colorless optimization to improve stability. So the gain before instability can be increased using that trick that I explained before on the sparsity and spectral flatness. And last slide. So this is a report from a master student about how to use FDNs in a shimmer reverb. It's classical design, so you have pitch shifters, FDN, the long one, then a delay so that the harmonics will fade in a bit later, and then a shorter FDN. So we looked at this, we were like, yes, but it's a bit too conventional. Can it be more compact somehow? Can we like do this in one single FDN? Probably yes. And there is a master student that worked on it this summer, but she hasn't finished her thesis, so this is still a work in progress, and I'm gonna be very vocal when we will release it, because it's very, very fun. So yeah, still work in progress is the main thing that I'm thinking about lately. Yeah, so in conclusion, just one sentence. The feedback delay networks are versatile architectures, and using machine learning, we can achieve more natural reverb and expand their capabilities to a wider range of applications. This is what I wanted to convey, and I hope I succeeded. Let's see. Yeah, if you're interested in what we're doing at the Acoustics Lab, please check out our website. And if you need some FDN and DDSP code, I try to put as much stuff as I can on my GitHub. And yeah, thank you so much.